Now that we've added the inductor as a new circuit element, we want to start to think about what happens when we put that inductor in with other elements into a circuit. And so we'll start by connecting inductors and resistors. So we'll start with what are known as RL circuits. Well, like what we saw with RC circuit, when we connected capacitors and resistors, when we connect inductors and resistors with a battery, we have a time-varying circuit. And so, of course, there are a couple ways in which we're going to choose to deal with time for an RL circuit in this course. One way is that we'll deal with what's known as a series RL circuit. It's simply a battery, a single resistor, a single inductor connected in series, and a switch to close the circuit. The other option is we can create complicated RL circuits. But we're going to do the same thing with RL circuits that we did with RC circuits, which is when we have a simple circuit, we can let time be more complicated. When our circuit is really simple, we can calculate out what are the current and voltage drops across the resistor and inductor as functions of time. On the other hand, when we let our circuit get complicated, then we want to simplify what's going on with the particular points in time that we're going to look at. So instead of dealing with sort of any point in time like we will with our simple circuit, we're only going to focus on t equals 0, the instant you close the switch, and as t goes to infinity, when our circuit reaches a steady state. So let's start by thinking about our simple series RL circuit. So I've got a battery, it has a voltage of V, I've got a resistor with a resistance of R, I've got an inductor with an inductance of L, and when I close the switch, the voltage across the inductor as a function of time goes like some initial voltage value, e to the minus RT over L. So again, you'll notice there's an exponential decay term here. There's some initial voltage value that I need to figure out, but this expression gives me what the voltage value is across the inductor as a function of time. Well, to figure out what that initial value is V naught, I need to think about what's going on in my circuit as I close the switch. And I know that at t equals 0 seconds, my inductor acts like a broken wire. So when you close the switch, the inductor is going to oppose any change in current by generating a back EMF that keeps current from flowing through the circuit for that initial instant when the circuit's closed. Which means that at t equals 0, my inductor is acting like a broken wire. It's preventing current from flowing through the circuit. After that initial instant, the inductor will adjust to the change in current, and so current will begin to flow through the circuit. But if I want to think about the loop rule at that initial instant in time, so I'm going to pick up voltage across the battery, I'll then drop voltage across the resistor, drop voltage across the inductor, but of course if there is no current through the circuit at t equals 0, then the voltage drop across the resistor also has to be 0. So what this means is that the initial voltage across the inductor, that initial back EMF generated by the inductor, has to be equal to the voltage of the battery. So I can plug that in, and what I get is the voltage of the inductor as a function of time is equal to the voltage of the battery times my exponential decay, e to the minus RT over L. Again, I can plot that out. And what I also recognize is that I can pay attention to what's going on in that exponential decay term by combining L over R into what's known as the inductive time constant. So again, it gets represented by tau. Tau with an L subscript tells me that I'm talking about my inductive time constant rather than a capacitive time constant. And that's going to be equal to L over R, so I can rewrite this exponential as e to the minus t over tau. The back EMF generated by the inductor as a function of time is going to be equal to the voltage of the battery times e to the minus t divided by this time constant. And again, that time constant gives me sort of a third interesting point to look at when I think about graphing out the voltage across the inductor. So at t equals 0, the inductor is going to generate a back EMF that's equal to the battery. So the fact that it's generating its maximum back EMF that is equal to the voltage of the battery is what keeps current from flowing during that initial instance. But obviously, that voltage drops. So the back EMF decreases. And again, once we reach the one time constant, so L over R, the voltage of the inductor has fallen to 36.8% of its initial value. Once I wait long enough so that I can say that T is approaching infinity, my inductor's not generating a back EMF anymore. The current's simply flowing through my inductor as it's adjusted to the new current. Well, from my loop rule, again, once I get past T equals 0, now there is current in my circuit, so I can calculate out what the voltage across the resistor is. It's just going to be the voltage of the battery minus the voltage drop across the inductor. And we just said that that's got to be V times e to the minus RT over L. And so when I plug that in, I get that the voltage drop across the resistor is the voltage of the battery times 1 minus e to the minus RT over L. What I see here is that the voltage across the resistor increases. So it starts at 0. Initially, there's no voltage across the resistor because there's no current in the circuit. But as the current begins to build up in the circuit, more and more current flows through the resistor, which means the voltage drop across the resistor increases. After one time constant, it's up to 63.2% of its final value. And then as T approaches infinity, the voltage across the resistor reaches its maximum value, which again happens to be the voltage of the battery. Now that I know the voltage drop across the resistor, I can figure out what the current flowing through the circuit is, because again I know that V equals IR across that resistor. So just using Ohm's law and solving it for the current I get that the current's going to be equal to the voltage across the resistor divided by its resistance value. And so all that does is take my initial expression for the voltage value across the resistor, divide by R, and so I'm simply changing the constant sitting out front. It's now the voltage of the battery divided by R times the expression 1 minus e to the minus RT over L. You can see that the current running through the circuit also increases. So again, it starts at 0 because initially the inductor generates a back EMF so that no current's flowing through the circuit. But as that back EMF from the inductor increases, the current increases. At one time constant, it's up to 63.2% of the final value. And then as T approaches infinity, it reaches its final value, which in this case is V over R, the voltage of the battery divided by the resistance of the resistor. So summarizing for a series RL circuit. Again, I know from my loop rule that the voltage I pick up coming across the battery, I have to drop as I go across the resistor and as I go across the inductor. As I go across the resistor, that's going to be the current in the circuit times the resistance value of the resistor. As I go across the inductor, that's going to be L, the inductance value, times how the current is changing with respect to time. I can calculate out those three values, so the current in the circuit and the voltage across both the resistor and the inductor, by these three equations. Again, I know that the current is increasing, the voltage across the resistor is increasing, so both of these are V or V over R times 1 minus e to the minus RT over L. The back EMF from the inductor decreases as time goes on. As that happens, what that means, of course, is that the voltage across the resistor increases because the current increases, and the voltage across the inductor decreases because the rate of change of the current decreases. So how much, if you think about that graph in the current, it flattened out as time went on, which means that its rate of change decreased. The rate of change of the current decreasing is part of why the voltage value of the inductor decreases. Again, in terms of my two special points in time, at T equals 0, there's no current in my circuit, so no voltage across the resistor, and the inductor is generating a back EMF that's equal to the voltage of the battery. Once I reach steady state, now what I have is I have a current that's equal to V over R. It's as if the inductor is just a wire, and so the current through my circuit is V over R. The voltage across the resistor is equal to the voltage of the battery, and of course there's no back EMF being generated anymore.